everybody. So now what we are going to do is we are going to do experimental study of photoelectric effects. All right. So this is how the study about photoelectric can be studied, right? Yes, we have this is experimental setup for photoelectric effect. So before I actually start, first we will talk about the experimental setup. So experimental setup is I have a vacuum tube, alright, I have a vacuum glass tubes. This is evacuated glass tube, means it is a vacuum tubes. This is what we call as a vacuum tubes. This is vacuum tubes. This is vacuum tubes. And then I have a photosensitive plate. This is a photosensitive plates. This is a P refers to our photosensitive plates, and C is a collector plate. This is what we call as a collector plate. That means electrons are being collected from a plate P, plate C, and P is a photosensitive plate. And now here, this is the voltage. This is the battery we are going to use. And this is the voltage regulator. This is what we call as voltage regulator, right? Voltage regulators. That means I can increase the voltage and I can decrease the voltage across PC. Alright, voltage is being applied across PC. P is a photosensitive plate and C is the collectors. And the voltage can be regulated by moving this arrow, right? And this is how you are going to measure voltage. This is how you are going to measure voltage. And then one very important thing is this is called a commutator. This is called a commutator. That means I can change the polarity. I can change the polarity of P and Q. P is initially negative. This is positive. All right. I can also make P a positive. I can also make P positive and C negative by changing this. Look at here, right? So if I say if this is connected to this side and if this is connected to that side, all right, and then what happens is that P become positive and then C become negative. If I do just the opposite. If I do just the opposite, if I connect this to that side and this to that side, then C become positive, P become negative. So the job of commutator is to interchange the potential, right, at P and C, or interchange the charge at P and C. This is very important, right? And then I have microammeter. This is photocurrent detectors. This is called photocurrent detectors. Photocurrent detectors, right? So if a photocurrent is more, then more electrons are removed. And if a photocurrent is less electrons are removed. So this is the experimental setup. This is the experimental setup, right? And then very important, I have a first window, right? Why we use a special coil means this coil window allow only specific frequency to pass through it. That normally this will allow a UV radiation to pass through it. So this allow a UV radiation to pass through it and then falls on a. That means this gives the selective, right? All right. So that's the point, right? This will allow only UV radiation to pass through it. All right. So this is what we have. What we talk about experimental setup, right? Now what we are going to what about the experimental study of photoelectric effects? So what we are going to study is now we are going to study the variation of photocurrent. Why? Because photocurrent, I just say a photocurrent is equivalent to electron emissions. photocurrent is equivalent to electron emissions. So once if you could detect a photocurrent, then there is the emission of electron take place. So that's the point, right? So now what we are going to study is how photo emissions depend on intensity of radiation. So first we would like to study how photo emission is determined by intensity of radiations, and then we would like to study what about the frequency of incident radiations. So we would like to study different factors, right, that affects the photoelectric emissions, and then we would like to study the potential difference between a plate A and C. All right, if I supply a potential difference, how it is going to, if I just reverse the potential difference, then what is the effect? And then last we would like to study, we are going to study is nature of matter. If I go on changing the metals and supplying a same amount of frequency, then we would like to see, right? So these are the main points which we are going to study, right? So the first we would like to do is that so first we would like to do is that intensity of radiations. Intensity of radiation. So I'll bring this here. So what I'm going to do here is frequency I'm going to fix. Frequency fix. Alright, then potential difference fix. So what I am going to change is I am going to change intensity. I am going to change intensities, and again what I am going to fix is metal plate is fixed. Metal plate is fixed. This is what we call as a control experiment. This is what we are going to control so many factors, right? And we are going to fix so many factors, and we would like to see one particular factor, and then see the effect, right? So I am going to change intensities. Intensity I am going to change. I am going to increase intensity, and what I am going to see. Alright, as intensity is, as I increase intensity, what I am going to see is what about photocurrent? Photocurrent in a sense, electron emissions, photo emissions. Electron emissions. I would like to see photoelectric emission. That's the point, right? So I'm going to fix frequency. That means I'm going to supply one particular light, and I'm going to fix the potential difference, and I'm going to fix metal surface, metal plate, and what I'm going to change is intensity, and then photocurrent, and then see what about the photocurrent, or that is what about photoelectric emissions. So how to increase intensity? By making it more brighter and brighter, making it brighter and brighter. So this is what we have. So what we found is, experimentally what we found is that the photocurrent increases linearly with the intensity of incident light. So this was found during experiment, right? As I increase intensity, right? So let's say intensity, as I increase the intensity, what is going to increase is photocurrent. Photocurrent that we could see, right? Photocurrent increase linearly. Linearly means they just directly proportional. They are proportional, directly proportional. Linearly they increase it. If photocurrent increase linearly, which implies that photoelectron emissions, the photoelectron emission increases linearly. That's the point, right? So hence we say that the number of a photoelectron emitted per second is directly proportional to intensity of light. So that means intensity determines number. If more numbers of if I increase the intensity, more electrons are being removed. All right. So that means more electrons are being removed when more intensity of light is fall on the metal surface. So that this figure out that the light is like a particle, right? So light goes on removing electrons. right? More light falls on it means more electrons are being removed. So that's one aspect of photoelectric effect. Now second what we are going to study is if you have a potential on a photoelectric effects. All right. So that means again I'll go back to an experimental setup. So now what we are going to do is I'm going to use three different light. I'm going to use three different light. So for one particular light, let's say frequency 1, let's say for first frequency, yes. So what we are going to do is I'm going to use one frequency of light. Let's say a frequency. This is the frequency we are going to use. And then what we are going to do is I'm going to use first intensity number 1. This is not high, this is intensity. So for intensity 1, and what I'm going to do is I'm going to increase the potential. Alright? I'm going to increase the potential between, so potential difference between P and C increases. As potential difference between P and C increases, what we found is more and more currents are found, right? Increases, more photocurrent. More photocurrent, right? But this increases, then it reaches what we call as saturation, right? What we call as saturations. Saturation point, right? Once you reach the saturation points, even if I increase the potential difference between P and C, no increase in a current took place. No increase in a current took place. That means what it means is that when a light falls on the metal surface, electrons are being removed. Electrons are not removed in a very regular way. Electron can be removed in all the directions, right? This all electron can be removed in all directions, right? So what happens if I apply potential difference? If I apply potential difference, what happens is that electrons are being attracted. So more and more electrons could reach C by applying potential. So once you could reach all the electrons from P to C, then there is no further increase in a photocurrent, alright, even if I increase potential difference. I am going to explain this, right? Why there is an increase in the photocurrents, alright? While the emission is such that they doesn't emit, right? Electron never emit in a regular way. They just scatter, right? Electron just goes in every possible directions. So by applying a potential difference, electrons are being directed. Electrons are being streamed toward. Electrons are being taken towards C. If more and more electrons are being attracted toward C, means photocurrent increases. However, if once all the electrons from P could reach C, then there is no further increase in a electron taking place. So therefore, this is what we talk about a saturation point. This is what we talk about saturation points. This is what we talk about saturation point. This is a saturation current. Saturation current. These are the saturation current. So I have first I do for a first intensity of light, and then I do for a second intensity of light, then I do third intensity of light, such that intensity goes like this. So the more intensity of light, more saturation current. More intensity of light, more saturation current. More intensity of light, more saturation. That means more electron can be removed. Right? More electron can be removed. More electron can be removed if intensity is greater. Now what I'm going to do is this implies potential difference between P and C are now reversed, right? Now I'm going to reverse the potential difference between P and C. Alright, see, look at here, right? Again, now I'm going to make this negative, I'm going to make this positive by changing commutator, right? So once if I remove this, so what I'm going to do is I'm going to reverse it, and I'm going to reverse it, make it positive. Initially it was negative, positives. If this is now negative, if this is positive, right? If this is if this is positive and this becomes negative, now electrons cannot readily move toward C. Why? Because there is a repulsion from C and there is attraction from P. All right. So there is a repulsion from C and there is an attraction from P. So therefore, this is very important, right? All the electrons never remove with the same energy. Some electrons with a greater velocity, higher energy, some electron with a less energy. So what happens is that I reverse the potential between P and C, and then goes on increasing. So once I reverse and goes on increasing, initially the weaker electrons are being stopped. Weaker electrons from a P are being stopped to reach C. If weaker electrons from a P are stopped to reach P, means photocurrent will decreases. And then I increase, then I further increase, then little stronger electrons are again being stopped, and photocurrents are still weaker. And then I still increase the potentials, and then the little stronger, right? Stronger electrons are being stopped, and then finally now only strongest electron could reach C. Now only strongest electron could reach C. Then photocurrent is very less. Now further I increase the potentials, and these potentials, let's say this potential is V0, and this potential could stop even the strongest electrons from P, alright, of reaching C. So therefore, once you reach that potential, no electron from P could able to reach C. No electron from P could able to reach C. And this potential is what we call as a stopping potentials. This potential is what we call as stopping potentials. Alright. So if I graphically do this, we are going to get like this. Alright. So this is going to become a stopping potentials. This is how we get a graph. So we have frequency is same. This is the frequency. For particular frequency, we have intensity 1, intensity 2, and intensity 3. Different intensity of lights. Different intensity of lights give rise to different saturation currents. Alright. However, what about the stopping potentials? But same. Alright. Stopping potential. And that stopping potentials determines the energy with which electrons are being removed. So therefore I say, intensity will change the saturation currents, but not change the stopping potentials. Why stopping potentials are same? We choose only particular frequency of light. So that is the reason, right? So therefore we have stopping potentials, right? So for a single frequency, so I just say for single frequency of light has one stopping potential, right? A single frequency of light with a different intensity has only a single stopping potentials. So this is one very important, right? Now third one, so this is what we have, what I have written explanation, right? Just actually I've done it now, so much explanations. However, we see, we shall vary the positive potential of P of plate A gradually and increase the resulting photocurrent each time. The photocurrent increases with increase in the positive potential at A until all the emitted electrons are collected by plate A. Then photocurrent become a maximum, which is what we call as a saturation current. This is what we talk about, saturation currents. Now we apply negative potential at, that means we are going to reverse it. Negative potential at A with respect to plate C, making it increasingly negative gradually. The electrons are repelled and only most energetic electrons could able to reach the collector plate A. The photocurrent found to decrease rapidly until it drops to zero. So now this is very important, right? The minimum negative potentials given to a plate A for which photocurrent stops or becomes zero is called cutoff or stopping potentials. So stopping potential is the minimum potential, and negative potentials are required to stop the most energetic electrons, or required to stop entire electron reaching collector plate, and that is what we call as a what we call as a stopping potential. And so stopping potential energy, right? This is stopping potential energy. This is a stopping potential. I say this is a stopping potentials. And this is a stopping potential energies. Stopping potential energy. And stopping potential energy is equivalent to stopping potential energy is equivalent to maximum kinetic energy. This is very important concept. Maximum kinetic energies. Maximum kinetic energy. Alright. This is what we call as Kmax equal to dV naught. This is very important, right? Now next, third study is the effect of a frequency on incident radiations. Now so far we kept frequency fixed. Now what I'm going to do is I'm going to fix intensity, right? Intensity fix. Intensity remain fixed. And then a metal remain fixed. Metal surface is fixed. So what I'm going to change is I'm going to change frequencies. Frequency vary. I'm going to change frequency, and then what I'm going to see, I'm going to see photocurrent. I'm going to change photocurrent. All right. So look at here. Now what happened is that if I fix intensity, since I fix intensity, we would be getting only single saturation currents. Single saturation currents. We would be getting only single saturation currents. Alright. Then now, that means, look at here. Again, I'll go back to experiment, right? So what I'm going to do is, I'm going to fix intensity, right? If I fix the intensity, what we found is, what we are going to change is, and then again, we are going to fix potential also, right? And this potential will change later, right? And then, what we are going to do is we are going to supply a fixed amount of intensity, and then we are going to change frequency. We are going to change frequency, right? So let's say I change a frequency like frequency 1, then frequency 2, then frequency 3. And all these three frequency will be having what we experimentally what we found is all these three frequency has same saturation currents. All these three different frequency has same saturation currents. All right. And then I reverse the potentials. Right. When I reverse the potentials and then go gradually increase, and what we found is that we got a different stopping potential. This is stopping potential 1, we would get a stopping potential 2, we would get stopping potential 3. So there is no effect. Frequency has no effect on saturation currents. However, frequency has effect on stopping potentials. Alright? Frequency 1 has a stopping potential V01, frequency 2 has a stopping potential V02, frequency 3 has a stopping potential V03. Alright. This is what we have. So this is what we have, right? So we have 3 different stopping potentials. And we also found that this is the smallest frequency, then alright. Mu3 is the highest frequency which has highest stopping potentials. So this is how it goes, right? This has a smallest stopping potential, then so higher the frequency, it requires greater the stopping potentials. Higher the frequency, greater the stopping potentials. The lower the frequency, lower the stopping potentials. Alright. And then I told you that stopping potential determines maximum kinetic energy. Alright. So that means this has highest maximum kinetic energies, and this has lowest maximum kinetic energies. In a way, this tells that the frequency is the one that determines the energy of light. Intensity is not the one that determines the intensity energy of light. It is the frequency of light which determines the intensity of, which determines the energy of light. So this is the point. So we would get a different light. So why single saturation current? Because frequency has no effect on number of electron being removed. All right. Frequency has frequency, since the frequency determines the energy. So with what energy electron can be removed is all determined by frequency. So this is all about. All right. Now so we obtain a different value of stopping potential for a different frequency of light, but same saturation current for same intensity of light for higher frequency. Stopping potential is greater, which implies greater maximum kinetic energy. This is what I told you, right? This is very important sentence. Now last part which we are going to do is, now what about? Now what I'm going to do is, I'm going to change metal surface. I'm going to perform my experiment on two metal surfaces, metal surface A and metal surface B. Metal surface A and metal surface B. And metal surface A has threshold frequency mu. Metal surface B has threshold frequency mu prime. That's the point, right? So let's say this is what we talk about. Just now we talk about work functions, and work function is determined also a threshold frequency, right? Work function or threshold frequency. This will be discussed this later, right? This is a threshold frequency. This is what we call a threshold frequency. Threshold frequency. Threshold frequency, threshold frequency. All right, so we say that. All right. So what I'm going to do is I'm going to plot a graph between stopping potential and a incident frequency of light. So what we found, this graph is very, very important, right? So I'm going to plot a graph between stopping potential and a frequency. We have I go on changing frequency of light. So first we'll do for metal A. All right. So if I say if a frequency, let's say I'll write here, right? For a frequency less than threshold frequency, if a frequency is less than a threshold frequency, then stopping potential is zero. Why stopping potential is zero? Electrons are not being removed. If electrons are being removed, only then we require stopping potentials. Since if a frequency is less than the threshold frequency, then electron cannot be removed from a metal surface. So therefore, this is what we have, right? So I say if for a frequency less than a threshold frequencies, stopping potential is always zero. Stopping potential is always zero. Stopping potential is always zero, right? So once the frequency is more than threshold frequency, this is threshold frequency, then stopping potential will increase. Increases with potentials. Then frequency will increases with frequency, right? So I say up to until you reach threshold frequency, no emission take place. So stopping potential always becomes zero, right? So once a threshold frequency is more than, once the frequency become more than threshold frequency, then the stopping potential increases with increase in a frequency. Alright, then I increase the frequency, stopping potential also increases. Alright, and then this is for this is for metal A. Let's say this is for metal A, alright, and metal A threshold, then metal B, again same, right? For mu less than mu naught 1, alright, stopping potential again zero, right? Now once mu is more than, then stopping potential will increase. Stopping potential will increase. Will increases with frequency. So that's the point, right? So threshold frequency tells about the nature of a metal surface. If a threshold frequency is lower or smaller, then the metal is more sensitive. If a threshold frequency is higher, the metal is less sensitive. And however, then once you reach a threshold frequency, once the frequency is more than threshold frequency, how it increase remains same. Alright? So the slope remains same. This slope for metal A and slope for metal B are same. Slope for metal A and slope for metal B are same. Slope for metal A and slope for metal B are same. And this has so much significance. This has so much significance. We will study this in while we explain Einstein explanation regarding a photoelectric effect. And then now if I extrapolate, if I extend this, alright, you will get here negative, right? You will get here negative. Alright, you will get negative, and that this tells about how, with what energy electrons are bound to nucleus. If this negative is less, electrons are less bound to nucleus. If this negative is more, electrons are more bound to nucleus. I'll show you this. This is what we have, right? So this is, alright. So this tells that this metal surface is more sensitive than this. This metal surface is more sensitive. Why? Because this is negative potential, right? Negative potential means less attractions. This more negative potential means more attraction. So this has so much sense. So this explains the nature of materials, right? This explains nature of materials, right? Now, overall, what we are going to show you is, so now this graph tells us that, stopping potentials, the stopping potential vary linearly with the frequency of incident radiation for a given photosensitive matrix. And then there exists a certain minimum cutoff frequency or certain minimum threshold frequency for which the stopping potential is 0. That's what we talk about a threshold frequency. If a frequency of light is more than threshold frequency, then only emission takes place. Oh, that's the point. And if frequency increases, then stopping potential also increases. So that's the one very, very important, right? And now again, the maximum kinetic energy of photoelectric wave vary linearly with the frequency of incident radiation. That's the right now. For a frequency of incident radiation lower than the cutoff frequency, no photoelectron emission is possible. All right. Even if intensity light, this has so much significance, right, regarding the photoelectric effect, right here. So that means energy is not at all defined by intensity. Energy is entirely defined by frequency of light. That's the point. So, right, that's the particle nature of light, right? And last, I would like to summarize entire experiments, right? So the summary in our textbook, this has done with the 4 points. So the points are written here, all right? So for a given photosensitive materials and a frequency of incident radiations, this is the first graph. Photocurrent is directly proportional to intensity of light. This is the first graph. Then second point is for a given photosensitive materials and a frequency of light. This is the second graph. Saturation current is found to be proportional to intensity of light. This is the second graph. And the stopping potential is independent of a stopping intensity of light. Stopping potential, right? With a different intensity of light, we have only single stopping potential. So that's graph number 2. And then for a given photosensitive material, there exists a certain minimum cutoff frequencies called a threshold frequency, below which no emission takes place, no matter how intense. That means that graph number 4, right? So that means we talk about work function for metal surface, for metals, and the energy supply is given by a light, right? And that light we will figure out in terms of threshold frequency. All right. So threshold frequency is corresponding to work functions, right? So if a light has this much threshold frequencies, then this would have to supply this much work functions. So that's the point, right? No matter how intensity that. And then the last point is the photoelectric emission is an instantaneous process without any apparent time lags. That means the emission is instantaneous. All right. So this tells that this 4 point tells that light has particle nature. Maybe in exam if they ask you write few points regarding light has a particle nature. If you could write all the 4 points, then you will get full marks. Okay. So with this, I'm going to stop. I explain all the 4 graphs, and then next class we would like to explain the photoelectric effects using Einstein this thing theory, right? So how Einstein explained photoelectric effects, right? So thank you, and next time we'll talk about Einstein photoelectric.